Okay, so hopefully you can see my screen now.
Yes, we can.
Okay, wonderful. Well, good morning, ladies and gentlemen. My name is Amirali Najafi. I am a research associate at the Center for Advanced Infrastructure and Transportation at Rutgers University. This morning's discussion, we're talking about developing asset performance and risk models. Let's see if my laser pointer works. Excellent. So we're going to talk about a number of different topics today. We're going to talk about the nature of decision making, the role of optimization, and some of the frameworks and mathematics that goes behind optimization. We'll talk about reliability analysis or risk analysis. We'll talk about degradation modeling, which is very important for various assets. And then we will wrap things up by really combining all the topics discussed into this idea of lifecycle planning, LCPs. So let's talk about decision making. The term decision making is really concerned with the process of selecting the best choice from a set of available feasible options. We typically do this to satisfy one or multiple objective criteria. Decisions made as a result of logical and scientifically structured processes are called rational decisions. This is not to say that if you're not following this process, your decision making is irrational, but if you're dealing with large, complex systems, expensive systems, you ideally want to have some sort of structured mathematical rigor behind your decision making. So, in decision making, we have decisions and we have outcomes. A decision is simply a choice among many alternatives, and outcomes are what comes through as a result of those decisions. Now, decision maker may basically want to express preference among the possible pairs of decisions and outcomes. This means that if there are many outcomes, we might want to rank these. So you can have one, two, three, four. We may want to have these rankings. Furthermore, decisions are typically made under uncertainty. So this means that the decision maker will have to make decisions based on risks associated with each of those decisions. There is also a utility or benefit that is associated with each of the outcomes. So the first step in the decision-making process is having a complete and clear understanding of the project objectives. This includes the purposes, the scope, the constraints. For example, if you have an engineering problem, perhaps the mechanical laws set the constraints of your system, right? Um, Also, if you are sometimes you are using a sequence of decisions to satisfy your objective. In those cases, we are dealing with dynamic decision situations. So that's important as well. The dependability of the decision is conditioned on our ability to predict the system's future performance. This step requires the construction of predictive models. So models are very important. This is where we start talking about degradation, where we talk about time to failure, and oftentimes there is uncertainty at this step as well. So we want to bring in probability theory into this step. Lastly, we talked about rational decision making. So the economic rationalization for the best alternative is often one that maximizes the expected utility. So we like to select the best design or operating alternative using some sort of optimization, and this is a mathematical process. We will now briefly talk about optimization under uncertainty within the context of decision making. Okay, so the mathematical optimization problem associated with any kind of complicated decision making is inherently constrained by the available resources we have. So in this setting, the decision variables X are determined so to maximize or minimize some predefined decision criterion. This decision criterion is often called an objective function shown here by f of x. The optimization problem also almost always has some sort of constraint. So here, H and G are the constraints of the optimization that the optimization is subject to, and they must be satisfied. Like we explained, if you're dealing with an engineering system, your mechanical laws, your physical laws are your constraints. You cannot beat the physical laws of the universe. In more complex engineering decisions, we might also solve complex trade-off problems. Oftentimes, we have a number of conflicting objectives, such as cost, performance, societal benefits, safety, etc. These types of problems are called multi-objective optimization problems. Now, so far, we've assumed that we know the nature of our decision variable and that they are perfectly deterministic. In most cases, this is not true. We, in reality, rarely know the true nature of the decision-making variable. So there's a lot of uncertainty. So we typically have to introduce some sort of random variable with some sort of prescribed probability distribution. So we had the original deterministic variable. Now we introduce a random variable. And this time what we do is we try to minimize the expected value of the objective function. Here, E is the expectation operator. So this is a probabilistic framework, whereas originally we talked about a deterministic framework. Now, to manage engineered systems, we'd like to optimize the performance over the course of time. Certain operational decisions may not be effectively made at the beginning of the project, such as all the operational details, etc. Therefore, we'd like to make a sequence of decisions over the course of time. This is where this notion of lifecycle planning, or LCP, comes in. We perform lifecycle planning as a study of a system's performance over the span of the system's lifetime. So we begin by looking at the system's benefit, its utility. It's shown here with the B. There are parameters to our system indicated by this vector P. There's often this delta function, which is a discount function that is used to compute the net present value of future gains and investments. We'll talk about that in a few slides. So here we're integrating because we typically like to sum all these systems benefits over the course of its existence. Now, the next thing we also want to do is we want to sum all the costs associated with this system or this asset. CI here describes all the incurred costs. These include failures, repairs, maintenances through the lifetime of the asset. So N here are the number of interventions. Now, of course, this is a probabilistic framework, so we are looking to take the expected value of this cost-benefit relationship, and we're looking to optimize that. Okay, let's talk about reliability analysis now. That's another important concept. So reliability analysis is a study of how a system fails. With any engineered system or asset, these systems are designed and built to perform a specific function for a specified period of time. But what's pretty much inevitable is that the system will eventually fail. Reliability analysis or risk analysis are quantitative methods of studying how a system fails. They're also significant in supporting decision making, and they help improve the system's overall quality, its safety, its performance, etc. So we have a system here that has two random variables, capacity C and demand D, each having a density FC and FD. So these systems, these random variables are indicated here. They have their own distribution. There's a mean, and there's the bell curve, the traditional bell curve distribution associated with most common systems. So In this context, a safety margin is the difference between our capacity and our demand. Notice that the capacity and demand overlap right here at some point. This is where the safety margin is breached. So in the context of reliability, um, reliability is the probability that our safety margin is greater than zero. We're looking for that probability. And also another thing we're saying here is we're assuming that the safety margin of zero is our limit state. So the mathematical relationship for reliability is as follows. It's basically an integration of the cumulative density. So this is the capital F is the cumulative density, the small f is just the density. And here we're assuming that capacity and demand are independent. They are non-negative random variables. If we make some additional simplifying assumptions about how our random variables are independent and normally distributed, then we can express reliability as 1 minus the normal distribution of this variable here, which is minus beta. This is a very commonly used variable. It's called the reliability index. It's very commonly used in engineering problems. So let's put everything together into the schematic here. So instead of having two curves, let's combine them into an overall, a combined safety margin curve that we have. When the safety margin is less than zero, we have the unsafe situation. This is when failures tend to happen. On the safer side, well, that's pretty self-explanatory. In this context, the failure probability is the area underneath here on the left-hand side in the unsafe region, and reliability is the area underneath the right-hand side. So of course, this is a distribution. It has a mean. It has a standard deviation. Reliability index as a multiple of the standard deviation basically indicates how far the mean of your system is from failure, from the unsafe region. So the larger your reliability index is, the further out you are from failure. Within the civil infrastructure domain, we ideally want to have beta to be 3.5 to a value of 4. Anything more than that, it results in your system being too conservative, too expensive. Anything less than that, then you start jeopardizing safety, performance, things like that. Okay, so let me now illustrate reliability in the context of the traditional degradation modeling that we've already seen through the lectures yesterday, and we'll see some today. So this plot you've already seen. We can basically take any asset class, any system, and express its performance over time through some sort of performance measure, through some sort of capacity. So at time 0, we have the original capacity of the system. That's V T naught. Over the course of time, nature does its thing. Degradation happens. Oftentimes, degradation happens through shock events, such as earthquakes, for example. So with this logic, we can calculate the remaining operational capacity of our system, which is V at time t is equal to the original capacity minus the degradation. So that's how we can identify what the remaining operational life is. Systems also tend to have a limit state that is not necessarily the zero crossing. So every single asset, every system tends to have its own limit state. And oftentimes when the limit state is crossed is when failure or the undesirable state is reached. So in this context, reliability is the probability that the capacity of the system remains above the limit state. So this is one way of thinking about reliability. There is a second way. We can think of the problem of reliability in terms of time. So reliability can be defined as the probability that the lifetime of our system remains above a specific period. So these two areas shown in the red are actually equal. And depending on the type of asset you have, the type of problem you have, you may want to think within the context of each of these two systems. And these are equivalent ways of thinking about reliability. So these two areas are equal. So yeah, FFT here, I guess, is the distribution with time, and L is the lifetime, is the total lifetime of our system. Okay, I think every other variable is described here. Excellent. Okay, let's talk about degradation modeling. Degradation modeling is another big component of decision making, lifecycle planning. When it comes to rate-based models, they are very commonly used for modeling progressive deterioration. So in rate-based models, damage is assumed to accumulate continuously over time. So if we have an asset with some kind of estimated degradation rate, what we can do is we can integrate this over the course of the period of interest, and we can find out what the accumulated degradation is. And here are some examples of deterioration. We have linear, nonlinear, piecewise. We could even have a combination of these. Now, the one thing to note here is we're looking at loss of capacity. We're not looking at capacity here, so the graph is inverted. So we're starting off at 0, we're going up instead of going down. So that's something else to note. For the case when the deterioration is linear, we can generally take the original capacity of our system, subtract the limit state from that, and divide it by the rate of deterioration, D. And that can give us the lifetime of our system, L. In more complex models, more complex systems, we typically assume that the rate of deterioration is a stochastic process. It's because there's uncertainty involved. And in reality, we don't really know what the rate of deterioration is within any system. So it's always good to admit that uncertainty and go with like some sort of a stochastic model. So let's talk about stochastic degradation now. Stochastic degradation process is a random degrading variable. One of the components of a stochastic process is called the index set. The index set is traditionally thought of as time. So time can be thought of as a set of integers, which makes time interpreted as a discrete process. Time can also be thought of as an interval, so it can be thought of as a continuous process. There's also another set called the state set, or often called the state space, which is really the state is what explains the process that is under consideration. State can also be continuous. It can also be discrete. So generally speaking, discrete time systems are easier to deal with. They're mathematically simpler, whereas continuous time systems are require just a lot more mathematical rigor. So here are some of the examples of each. We have the Wiener process, Gaussian process, Poisson process, and within the discrete domain, we have Markov chains, very, very commonly used. This figure is very interesting. It talks about the different matches that can happen when your time and state indices are discrete or continuous. So depending on what you're modeling, the specific application, you may want to go with either of these 4 options. But it's a very nice illustration that I really liked. Okay, so of course, there are many degradation processes. I will cover 2 examples here for the sake of time. The first example is the Wiener degradation. Wiener process is a continuous time, continuous state, stochastic process. In its simplest form, it has the following shape. So there is a constant initial degradation. So if you're starting at some time t, you're not starting at the origin. You always have some sort of initial degradation that has already happened. There is a mean drift, which is the general directionality of the process. There's a variance. There is a standard Brownian motion, which sort of describes the dynamics, the vibrations that are happening here. What's interesting about the Wiener process is that it has anti-degradation. So sometimes you can go up. This does happen within some systems, within some assets. So it's good to have it within your modeling capability. And then we can talk about the more stochastic mathematical side of things. The Wiener process follows an inverse Gaussian distribution by making some assumptions such that mu of t is equal to mu t. The lifetime density becomes as follows. So all you need to know here is that we have a very complete understanding of the different probabilistic processes. And of course, with any of these processes and their corresponding data sets, we have to find fits for all these parameters. We have to estimate all these various parameters. Okay, so the next example is Markov chains. Markov chains are based in the Markov property. Markov property is very often thrown around, but it's a really simple concept. It basically suggests that the conditional probability of any future state is dependent only on the current state, not the ones before. That's all Markov property means. So at any time index n, the future process is independent of the past and only dependent on the present process or state. There's also X here, which are the states of our system, and there are indices that describe the discrete time events. So given the Markov property, what we can do is we can introduce matrix P, often called the transition probability matrix. And a transition probability matrix, or a TPM, pretty much describes the transition from one state to another, from state I to J. These are often consecutive steps. That's why we call this one-step TPM. So what we can do is we can then multiply a probability vector which represents the probability of a system being in any particular state, shown here by P naught. We can multiply that by the multiply this probability vector by the TPM shown here, n many times. That's why we have the exponents n. And we do this to identify the probabilistic states of the system at index n. So there's a little bit of mathematics involved here. So given some sort of arbitrarily provided TPM, we have this. We're going to start with some sort of state probability vector. Typically, we start at the pristine, the original state of the system. So the first element of the state vector is 1. That means the system is 100% in excellent shape. So, the first element is, yeah, and of course, you can have different definitions. They're not necessarily what I have here, but you can have a system being graded into 5 different states in terms of, in a probabilistic sense: excellent, good, average, poor, failure. And then we do the multiplication. So at index 1, we are 31% in excellent state, 15% in good state, 37.5% average, and it goes down. And by the time you reach the 25 index, 25th index, you are pretty much looking at failure. And we can also plot the failure probability. Now, I do want to add, for every system, the failure probability, this curve will look completely different. So in some systems, it will be a lot more gradual. In this system, failure tends to happen fairly quickly. So this is not always true. Okay, so let's slowly bring it all together and back to this notion of lifecycle planning, which is so important. LCP is pretty much where all the discussed decision-making tools come together. LCP is an important criteria for comparing various project investment alternatives. LCP is a tool for establishing optimum management policies. So it's a very important tool. LCB pretty much integrates the benefits derived from a system's existence. So here we have B, which is the benefits of the system, P are the parameters of our system, and TD is the lifetime of the system. So here we have the life cycle cost formulation as well. So we're going to start looking at the construction costs. These are the initial costs, which include planning, design, construction. Note that this particular system has two different limit states. There's a serviceability limit state, there's an ultimate limit state. So that's possible within different assets, different systems. The serviceability limit state means you're aiming for optimal performance. The ultimate limit state means failure, if you pass that threshold. So there's often other costs as well, including preventative maintenance, required maintenance that need to be considered. They are shown here with the CL. There is also decommissioning. So decommissioning costs are also very important. Decommissioning is often not a function of the parameters of the system. It's simply a cost that is added to the end of the project. So we don't see P here. Okay, so the LCP cost-benefit relationship needs to be optimized. So if you look at it from a probabilistic point of view, we have to take the expected value of that cost-benefit relationship and maximize it in order to make the project or the asset feasible. If the maximization is successful, we should end up with parameters that are optimal. So we have P optimal. Another thing we should consider in many projects in many asset classes is this notion of discount rate. So a discount rate is a rate used to discount the future cash flow back to its present value. For obvious reasons, if I offered you $100 today, it will be worth more to you than if I offered you $100 3 years from now. So it's good to consider discount rates. Within the corporate sector, market interest is what typically determines the discount rate. In infrastructure, which uses social projects, the private rate can't really be applied. So we typically have a lot more distortions, a lot more uncertainty. So there is a social discount rate that is often applied. The social discount rate is on the order of 3 to 7% in developed countries. It tends to be a little higher in developing countries. And so we can incorporate the discount rate into the former setup from the last slide by basically taking the various costs at different time steps, multiplying them by the discount rate formulation, shown here with the exponential function, and we can get the total expected discounted cost for the nth intervention. So a little bit of mathematics involved, but these are independent elements that are pretty much put together, so they're easy to work with. Okay, so we mentioned that given benefits and cost of the system, these things are distributed over a time horizon defined by the lifetime of the system. However, in the graph that I have here, which is oftentimes used for lifecycle planning, we don't see a time horizon. We only see dollars. We see the parameters of the system. So we need to discount all the costs and benefits of the system or of the asset to a point in time. Generally speaking, that point in time is the start of the project or when we start analyzing the asset. And this approach is pretty much called net present value evaluation. So we have the benefits of our system. We have the costs associated with the initiation of the system or the asset. There are costs associated with maintenance and losses. And we have the complete objective function, which is the cost-benefit analysis. And ideally, what we want to do is we want to stay in this acceptable region, which is where the objective function has a net positive value. So this is what makes the project or the asset feasible. And if we do things perfectly, we can get the optimal parameters, where this is where the peak of the objective function tends to happen. So I guess the takeaways from this slide are that discount rates can greatly affect the result of our LCP. We mentioned social discount rate, which is really how a society values an asset in its current condition, as opposed to its potential future states. It's very important to really consider the various benefits, costs of the system in order to have a very complete image of the overall life cycle.